Good evening, everyone. Welcome you all to Week 5 live interactive session of the class Introduction to Operating System. So today the topic that we will be discussing is process scheduling. So before that, let's first take one look at the various states of each process. So we have seen that initially the process will be in the new state or in the s- sorry. Yeah, it will be in the new state when the process is created. Then it moves to the ready state. And from the ready state, the process goes to the running state. Now, from the running, it can come to the blocked. It can also come back to ready state. From block, it can come to ready state. Mm. Okay. So, where the significance of process scheduling comes is when a process is moving from ready to running state. So, when do we say that the process is running? The process starts to execute when it gets the CPU. So, we know that there will be in a system there will be multiple processes which will be waiting in the ready queue. This is a queue. There will be multiple processes in the queue and all of these processes will be waiting for getting the processor for execution. So, which process will get the CPU first? And on what order? What is the algorithm used to do that, and who does it? Is what we will discuss. So, the person who takes care of assigning the CPU to the processes is the scheduler. We call it CPU scheduler also. And we have various scheduling algorithms using which the various processes from these queue will be assigned the what to say assigned the CPU. Okay. So some of the processes that are there in the ready queue will be more compute intensive processes, and some processes can be IO intensive. So, for example, the Excel sheet kind of an app, if you are doing an editor app that you are like you are doing some documentation in the Google Doc or in the MS Word or so. So, those are more IO intensive processes. Whereas, like you have some computation being run behind, like some you wrote some program to sort some numbers or what to say some compilation kind of programs. Those are like which will be running in the background that are compute intensive. They won't be taking much of an user input kind of thing. Okay, so there are different types of processes. Some will be IO intensive and some will be compute intensive. So when we have this IO intensive processes, right? When they go to the running state, they will run for a short span of time, short CPU burst. They will have short CPU burst or CPU time, and then they again go for the input output operation. So from the running, these IO bound processes will go from the running state to the block state very quickly. Then they will be having running for a very short period of time. Whereas in case of compute intensive, they will normally have large CPU burst. Okay. So there are different kinds of algorithms that takes care of the scheduling the scheduling the process to the to the CPU. And the intention or the aim of these algorithms is to what is the final goal? We want all these processes which are present in the ready queue to run quickly and complete it, right? We don't want them to wait for a long period of time. So we want these algorithm to run such that all these processes that are there in the ready queue quickly executes and comes to completion. So in that sense, there are certain aims or goals for all these algorithms, all these scheduling algorithms. The first aim or intention is to minimize the waiting time in the ready queue. The other intention is to maximize the CPU utilization. So we don't want the CPU to stay idle because the algorithm didn't schedule the processes in the proper order. Then we also want to maximize the throughput, the number of processes completed. That also needs to be maximized. Then we want to minimize the response time and also the turnaround time. And then we also want the algorithm to be fair towards each process. So all the processes should get a fair share of CPU. So these are the major goals or aims of this CPU scheduling algorithm. So let's take a look at couple of these algorithms and also see a couple of numericals and solve them using these scheduling algorithm. So the first one that we will discuss is first come first serve. Second one is shortest job first. FCFS, we normally call it FCFS. This is SJF. Another version of this algorithm is shortest remaining time first. That is SRTF. The other one is round robin. Okay, first we will see through all these four. Okay, so as the name suggests, first come first serve is a, so whoever comes first to the, so if this is the queue, first comes here, second comes here. You know the property of the queue, right? In a queue, we insert on one end and we delete from the other end, right? So we will insert on this end and we will take from this end. That is how the FIFO cube works. So first this process comes, then this comes, then 3, then 4, then 5, like that processes will come. And then when we are, so this will be the ready queue and the processes will be, sorry, the processor or the CPU is allotted the order in which the processes came. So who came first? One came first, then two, then three, then four, then five. So first P1 will be given the CPU, then P2 will be given, then P3, then P4, and then P5. So the order in which the request came to the ready queue, in the same order the CPU also will be given. Okay, so let's see an example. So that is the first come first serve algorithm. So suppose we have P1, let's see, let's take an example, P1, P2, P3 and P4, and they have come in the arrival time. They have reached the ready queue at 0, time 1, time 2 and time 3, and the burst time is the time needed to complete this process is 7 time unit. This is 4, this is 2 and this is 5. Now, as per the first come first serve, how it happens is we normally represent the CPU scheduling using a Gantt chart. So it's like a timeline kind of a graph. So this starts from 0. So as per this arrival time, we know that in the ready queue, first P1 came, then P2 came, then P3 came, and then P4 have come. So at time 0, P1 is there in the ready queue. So P1 will be given the CPU. Okay, then P1 will execute for 7 time units. It will be execute for 7 time units and then P1 will complete. Now after so P1 is done. Now after 7 time units, P2, P3 and P4 all of them are in the ready queue. So now P2 will be given the CPU because it is there in the queue now. In the top of the queue, so in the front of the queue, P2 is there now. So P2 is given the CPU. So P2 will execute for another 4 time units and P2 will be removed from the queue. Now, who is in the front of the queue? P3 is there in the front of the queue. Now, P3 will be given the CPU. P3 will execute for 2 time units. And after that, P4 will be given the P4 is there in the front of the queue and P4 will be given the CPU. And P4 will execute for 5 time units. Okay, so now it started from 0. At 7 time unit P1 completed. Now P2 will complete at 7 plus 4 which is 11. At 11 time unit P2 will be completing. Now P3 will start at 11 and it will execute for 2 time units. So P3 will complete at 13 and P4 will complete at 18. Okay, so now if you want to see how much time each of the process is waiting, so let's see the waiting time of each of these processes. So how long did P1 wait?
Ma'am, for 0 millisecond.
So waiting time for P1 is 0 time unit. How much time did P2 wait?
6 millisecond.
Yes, it waited for. So the time when it got the CPU, that is 7, and then its arrival time. So 7 minus 1, which is 6. P3, how
Nine
much time?
millisecond.
So P3 got the CPU at 11. And what time did it came to the queue? At 2.
2.
So 9. And P4,
10
13 minus
milliseconds.
3, which is 10. Now what will be the average waiting time here? So the average waiting time here is 6 plus 9 plus 10, which is 25 by 1, 2, 3, 4, 4 processes. 25 by 4, which is 6.25. Okay. This is about the average waiting time. So waiting time is the time spent in the ready queue waiting for the processor. Okay. So in first come first serve scheduling, this is a non-preemptive scheduling scheme. So what does non-preemptive means that if we give the CPU to a particular process, we cannot forcefully take back the CPU. Either the process has to run to, the CPU must be given voluntarily by the process. So that can happen in two scenarios. Either the process exit or the process goes for an input IO operation. So in case of preemptive scheduling from ready state, so sorry, from running state, either the process will go to exit or the process will go to blocked. Running say it will never go to ready again. In case of it will not go to ready. In case of non preemptive scheduling. Okay, so if P2 wants to get the CPU before, either P1 should have gone to the block state doing some input output operation, or P1 has to run to completion. Only then the next process will get the CPU. Okay, so this is how non-preemptive scheduling works. Now let's additional to average waiting time, another time that people will normally be interested in is the turnaround time. Turnaround time is the total time that is taken by the process for completing its execution. Okay, so turnaround time is normally the time when the process completes its execution. Okay, so now let's see what is the turnaround time of P1, P2, P3, and P4. So, what is the turnaround time of P1?
I'm 7.
It is 7. Correct. What is the turnaround time of P2?
11.
That is the time when it completed, right? But what time did P2 come to the waiting queue?
1.
So that completion time minus arrival time. That will be the turnaround time. So turnaround time is equal to exit time minus arrival time. So it comprises of execution time plus waiting time. Okay, so that is the reason we are. So here, if we take 11, okay, of this 11, P2 was waiting for only 4 is the execution time of P2. And what is the waiting time of P2? It is 6. So turnaround time is only 10. Okay. So another easy way is to do the find the exit time, that is 11, and subtract it from the arrival time. So for P2, for P1 it is 7 minus 0, which is 7 itself. For P2 it is 11 minus 1, which is 10. How much it is for P3? What is the exit time of
11.
so it is 13 minus arrival time is 2, which is 11. And for P4, it is 18 minus.
350.
So now what is the average turnaround time? 7 plus 10 plus 11 plus 15 by 4. Okay, you can compute the value. So this is one example of how the FCFS scheduler works. Now, if here it is clearly told that the arrival times are different, 0, 1, 2, 3. Now, if all the process comes at the same time, then one of the random order will be taken. Okay. So as discussed in the class, for example, okay, I will write down the example. Process, arrival time, and burst time. So P1, P2, P3, P4, all of them are coming at the same time. 7, 4, 2, 5. Now if I take the execution order as P1, P2, P3, P4, I will get one waiting time, turnaround time, response time, etc. And if we go like now there is no clear cut indication of who came first, right? So if we go like P3, P4, sorry, P2, P4, and P1, we will have a different order and different this one. What to say? Average waiting time and turnaround time. So this is one thing with respect to first come first serve scheduling. And the main advantage of the scheduling is that it is simple and it is fair enough. Like end of the day, nobody will be waiting for a long duration of time in the queue. The queue will become shorter and all the process will get the CPU. The only problem is that if suppose there is a if suppose instead of P2 being 4, if it is 100, then probably if I am going taking the order P1, P2, P3, P4, P3 and P4 will have to wait for until this long CPU burst process gets executed. So that is the only thing. But the major disadvantage with this FCFS is that here the waiting time depends on the arrival order, and sometimes short processes. For example, we had like this as 700, this is 100, this is 2, and this is 1. These short processes, which needed only 2 and 1, had to wait so long in the CPU because they came little late. So normally for FCFS scheduling, the average waiting time is higher, but otherwise it is a simple mechanism. We can see maybe one or two more examples on FCFS scheduling and then move to shortest job first. Yeah. So process, arrival time, and burst time. P1, P2, P3, P4, P5. The arrival time is 3, 5, 0, 5, and 4. And the burst time is 4, 3, 2, 1, 3. So, based on the arrival, the ready queue will look like. How will the ready queue look like? Who came first?
P3.
Yeah, P3 came first. After that,
P5.
P3
P1.
came first. After that, P1. After that,
P5.
P5,
P2 and P4.
P2 and P4. So this will be the order in which the processes get scheduled. So let's draw the Gantt chart and then come up with the average waiting time and turnaround time. Okay. So we start from 0. So P3 gets executed first. P3 executes for 4 time units. After that, P1 executes for, P3 executes for 2 time units. 2 time units. After that, P1 executes for 4 time units. Then P5 execute for 3 time units. Then P2 executes for 3 time unit, and P4 also P4 execute for 1 time unit. Correct? So let's mark it. So 0. So the completion time of P3 is 2. Completion time of P4. Okay. We can write it down. It's better. Completion time of P3 is 2. P1 is 4 plus 2, 6. P5 is 6 plus 3, 9. P2 is 9 plus 3, 12. And P4 is 13, right? Is this correct?
Yes, ma'am.
Sure.
Yes, ma'am.
So this is actually wrong. This is wrong. Okay. So let's start again. So you have to pay attention. Okay. So first, who came? P3 came at 0. Okay. P3 executes for 2 time units. Now at what time is P1 coming?
At 3.
At 3, right? So after P3 executes, so P3 executes and complete at 2. Now P1 is coming only at time 3. So this one time unit, nobody is there. So this is free. This is idle. The CPU stays idle until P1 comes. Okay. So after that, now P1 comes. Now P1 will execute for 4 time units. Now this is the completion time of P1 is 7. So by 7, all of them have arrived. Now we can, so whenever you draw the Gantt chart, right, you have to make sure that by the time P3 completes, there is somebody who have arrived in the ready queue. Okay. So you can check that by looking at the arrival time of the second process. So this P1 arrived at time 3 only, at 3 seconds, whereas P3 completed at 2 seconds itself. So after P3 was completed, the ready queue was empty. Okay. So the processor had to wait until P1 came. Okay. This is clear.
Yes, ma'am.
Now P5 will execute for 3, P2 will execute again for 3, and P4 will execute for 1. 7 plus 3, 10, 10 plus 3, 13, and this is 40. Okay. So now let's do the average turnaround time. Average turnaround time and P1, P2, P3, and P4. So turnaround time and waiting time. So the two formula that we use is turnaround time equal to exit time minus arrival time. And waiting time is actually, we can also find it from turnaround time. Turnaround time minus burst time. That will also give us the waiting time. Okay. So let's compute the turnaround time for P1. So P1 is getting over by 7. Okay. And what time did P1 come?
One.
P1 came at 3. So 7 minus 3 is equal to 4. P2 is 13. That is the exit time of P2. And P2 came at 5. Arrival time is 5. 13 minus 5 is 8. P3, where is P3? P3 completed at 2. So 2 minus arrival time of P3 is 0, which is 2. And P4 completed at 14. Arrival time of P4 is 5, which is 9. Correct? We have P5 also. P5 completed at 10 and P5 came at 4, which is 6. Now let's see the waiting time. Waiting time is nothing but turnaround time minus burst time. So turnaround time is 4 minus burst time of P1 is 3, which is 1. Okay. Sorry, burst time of P1 is 4. I took this. Yeah, so burst time of P1 is 4, which is 0. So waiting time for P1 is 0. Same way P2, the turnaround time is 8 and its burst time is 3, which means that wait time is 5. P3 is turnaround time is 2 and its burst time is 2. So its waiting time is 0. Then for P4, turnaround time is 9 and its burst time is P4's burst time is 1. So its waiting time is 8. And for P5, the turnaround time is 6 and its burst time is 3, which means it is waiting. We can, if you don't want to use the formula, you can figure it out by your own also. Okay. So if you see that P3 came at 0 and immediately it got the CPU. So like it is waiting for 0. It's easy for FCFS, but when we go for round robin and all, we will interleave the executions of different processes. So waiting time will be little in the front, little in the middle, little again. So there will be then doing it manually would be little tricky. So it's better, but finding the turnaround time is pretty clear because that is the exit time when the process completes the execution, and we also have the arrival time. So turnaround time is the total time that the so if you see this formula, turnaround time is the total execution time, which is nothing but the burst time and the waiting time. So we are just using this equation. So what will be waiting time? Waiting time will be total execution. Sorry. You keep this waiting time and take this to the left hand side. So it will be turnaround time minus total execution time, which is nothing but the burst time. So this is how actually we get. Now you can average it up and find out what is the average turnaround time and waiting time. So I think that I will skip. So it will be, you can just do this off. Okay. Shall we see one more example?
Yes, ma'am. Yes, ma'am.
Okay. Okay. Then maybe a simple one. P1, P2, P3. Arrival time is 0, 3, and 5. And burst time is 2, 1, and 6. Okay. So let's do this. Let's draw the gun chart. So at 0, who came? Who came first? P1 came first. So at 0, P1 starts executing and it will execute for 2 time units and it will complete by 2. Okay. Now at this time, at 2, do we have anybody arriving? P2 and P3 is in the ready queue at the end of P1's execution, or is the ready queue empty?
Ma'am, ready queue is empty for 1 millisecond.
Yeah, so ready queue is empty for 1 time unit. Then now when it is 3, P2 is in the queue and P2 will execute for 1 time unit, correct? Yes or no?
Yes, ma'am.
So P2 will complete its execution by 4 millisecond or by 4 time units. Now what time does P3 comes?
At 5.
So is the ready queue empty or do we have any process in the ready queue?
Empty for 1.
Again, 1 time unit, the ready queue is empty. So the CPU will stay idle. Now after that P3 will come and it will execute for 6. Okay. Now can you quickly tell me the turnaround time? Turnaround time is equal to exit time minus arrival time. So for P1 it is 2 minus 0, which is 2. For P2, 4 minus 3, which is 1. And for P2. And for P3, it is 11 minus, it is arrival time 5, which is 6. Now let's see the waiting time. What is waiting time is turnaround time minus burst time. So it is 2 minus 2, which is 0. 1 minus 1, which is 0. And 6 minus 6, which is 0. So none of the processes had to wait in the ready queue. So whenever they came, the CPU was idle and quickly they were put into execution. Okay. So now let's go to the next scheduling, that is shortest job first. So, so SJF is the what it does is it will uh, look at the burst time of all the available processes, and it will choose the one with the smallest burst time. For example, if all the processes come, for example, in the above example, if you see P1, P2, and P3 comes, all of them are in the ready queue at the same time, and their burst time is 216. So, what shortest job first do is it will take the process which will have the shortest burst time. So, so you can think that the SJF scheduler will sort it based on the, I mean, arrange it in the ascending order for the burst time, and then schedule them in that order. So, the one who have the smallest burst time, then the one
I'm
with the
P1.
next P1, and then P3. So, they will be scheduled in this order. Okay, so that is the shortest job first. This is the non-preemptive version again. So here what happens is the scheduler will look at the ready queue. From the ready queue, it will choose the process with the shortest burst time. And once the process starts executing, then the process it will continue. It will be like there is nobody will stop the process in between. If a even smaller process comes, nobody will stop it and then give the CPU. So that's another, the preemptive version is the shortest remaining time first, that will come to it. But this is the simple non-preemptive version wherein it will check the ready queue for the process with the shortest burst time. Okay, so the advantage of SJSF is it has the minimum waiting, average waiting time, minimum average waiting time. So that is one advantage, and also minimum average response time. So that is achieved in shortest. The disadvantages, it is a little difficult in practical scenarios, because if I have to do this, you need to know the completion time or the burst time of each process, which actually is not uh, possible, right? It's difficult to predict the burst time. And another thing is, if I have one long process, another disadvantage is something called as starvation. So for example, if I have like processes some P1, P2 up to Pn, all of them have very short burst time, like 1 2 3 2 1 4 etc. All the burst times are less than 10 only, but I have some one or two process with burst time which is like 700 or 500. So these processes will have to wait until all the short processes gets executed. And if the newly coming processes, if the new coming processes are also short, then they end up waiting infinitely. So this is called a starvation. So this in the disadvantage of SJF is like it can actually cause starvation of long burst time jobs. So let's see an example. Maybe one from the slide itself. P1, P2, P3, P4. Give me a minute. Yeah, sorry for that. So, yeah. Okay, so P1, P2, P3, P4, and the arrival time is 0, 2, 4, 8. And the burst time 7, 4, 2, 1. Okay. So now if you see the ready queue, so initially at 0, we have only this one process available, right? So of the available processes, the scheduler will choose P1. Okay, now if we scheduler, so if we make it, this is 1, 2, 3, 4, 4. Okay, so now P1 came when it was 0 itself. So in the ready queue, no other process is there. So P1 will be scheduled and P1 will run for 7. Okay. Now in between, P2 comes at 2, P3 comes at 4, and P4 comes at 8. Okay. So now when P1 completes, we have P2 and P3. So when P1 is completed, we have P2, P3 in the ready queue. Okay. Now of the P2 and P3, P2 have 4 time units and P3 have 2 time units, correct? So of this, which one will get the execution? Which one will be executed?
Ma'am, first process 1 will execute,
Hmm?
then process
Yeah.
3, then process
Okay.
4, and lastly process 2 will execute.
Okay. So after this, now process 3 will execute, right? Process 3 will execute. This is P1. Then after process 3 is done, P4 is already there. Right now P2 and P4 is there in the queue. P4 came at this point. So now we have P2 and P4 in the ready queue. So P2 takes 4 time units and P4 take 1 time unit. So which one will be executed next?
Ma'am, P4.
So P4 will now be executed. So P4 will be executed for this time unit, and then after that
P2.
P2 will be executed. So this P2. Okay. So from the available processes, it will choose the smallest one. So that's how shortest job first works. So let's see some more examples of SJF. Okay. Okay, this is example. Right. So this is SJF. So process, we have P1, P2, P3, P4, and P5. Now this is arrival time, and this is burst time. So P1 3 1 4 0 2 and 1 4 2 6 3. Okay. Yeah. So now let's do our calculation. So first, who came? P4 came. So let's first do this arrival ka draw. Let's draw the arrival order. So first P4 came at 0. Then at 1 who came? P2 came. Then at 2 P5 came. Then 0, 1, 2, 3 who came? P1. And then 4 at time 4 who have come? P3. Is this correct? P4 came first, P2 next, P5, P1 and P3. Okay, so this is the order in which the processes came. Now let's draw the Gantt chart. Okay, so initially we have only P4 in the queue, correct? So P4 will be scheduled. So P4 will be scheduled and P4 takes 6 time units. So P4 will execute and it will execute for 6 time units, and by the time P4 completes, it's already 6 time units. Okay. And if you see here, all our process have come by then. Okay. So by the time P4 completes, if you look at the ready queue, we will have P2, P5, P1 and P3. P2, P5, P1 and P3. All of them are in the ready queue. Now we need to choose the one with the smallest burst time. Or we can arrange, because by the time P4 completes, all of them are in the ready queue. So now we need to execute in the increasing order of burst time. So maybe we can arrange them in the increasing order of burst time. So who have the smallest burst time? It is P1. Then the next
P3,
smallest is P3 and the next
P5,
smallest is P5 and
P2.
P2. So now we will execute in this order because already the ready queue have all these processes in place. So now after P4, P1 will execute for 1 time unit. So it is 7. Then P3 will execute for 2 time units. Completion time is 9. Then P5 will execute for 3 time units and P2 will execute for 4 time units. So completion time 16. Okay.
Yes, ma'am.
Yeah. Now let's see the turnaround time, and just for this example we'll compute. For the next examples, I think I will skip the turnaround time computation because by now you should be knowing, right? Turnaround time is, what is it? Turnaround time? What is the formula?
Completion time minus arrival time.
Exit time minus arrival time, or completion time minus arrival time, and waiting time equal to turnaround time minus
Turnaround time minus execution time.
that is burst time. Okay, so now let's see that turnaround time and waiting time. So for P1, P2, P3, P4 and P5. So P1, what is the turnaround time?
4. Ma'am, 4.
Yeah, 6 minus 0. It's okay. For P1, it is 7. 7 minus
Minus
what time did
3. Ma'am,
3?
3.
Okay, which is 4. So P2,
16 minus 1,
16
15.
minus hmm,
P3, 9
P3,
minus 4, 5. P4, 6 minus 0, 6. And P5, 12 minus 2, 10.
okay. Now for waiting time, it is turnaround
Ma'am,
time
6
minus
plus 6.
burst time. Okay, right?
Yes, ma'am.
Yes, so now you can take the average. Okay, maybe one more question. One more example we can see for SJ. It's going to go number. I think we'll go to shortest job, shortest remaining time. We'll see the example from that. Okay.
Okay, ma'am.
So the next preemptive version of shortest job first is called as shortest remaining time. So here what happens is, oops. So okay. So here what happens is now if you see that we have mm, hmm. So here if a one process is executing, a process is executing, and if a new process comes to the ready queue, ready queue whose burst time is less than this process remaining time, then process is preempted. Preempted means moved out of CPU, and new process is okay. Let's see an example. That is, we have P1 and P2. P1 comes at 0 and P2 comes at 2. P1's execution time is burst time is 8, whereas P2's burst time is 4. Okay. So now P1 is executing 0. P1 is executing because initially nobody was there in the queue. P1 was given. So P1 will execute. Now in the ready queue at time t equal to 2, at time equal to 2 unit, P2 will come, right? Now when a new process comes to the ready queue, we will check the remaining time of P1. What is the remaining time of P1? It is 8 minus
6.
2, correct? 6. Now P2's time is 4. Now which one is smaller here?
P2.
So we will take out P1 and then we will give CPU to P2. Now P2 will execute for 4. Then after that, P1 will come back and execute for the remaining 6. Okay, so this is what is called as preemption. So if you see the process state diagram, we had the ready queue, we have the ready state, we have the running state. So currently P1 is in the running, and in the ready queue P2 came. Okay. Now when P2 comes, we do this check. 6 is less than 4. No, right? So P1 will be brought back to ready. P1 will come to ready and P2 will go to running state. This is what preemption does. Okay. We will forcefully remove this process out and give a new process, give the new shorter process the CP. Okay, is this clear?
Yes, ma'am.
Okay, then maybe we can see another one. So the advantage of SRTF is that it will again bring down, further bring down the average average waiting time and response time. But here again, the problem is we like initially we need to know the burst time of the new process. So that is the disadvantage here, which is not quite practical, knowing the burst time. Okay. So now we can see maybe one example and then move to round robin. This is this is great. Okay. Another example. So we have P1, P2, P3, P4, and P5. P1, P2, P3, P4, P5. Now arrival time, burst time. I will also mark remaining time. Thus we will keep filling it as and when we do the preemption. So arrival time is 3, 1, 4, 0, 2. Burst time is 1, 4, 2, 6, 3. Okay, so first let's order them in the order of arrival. 0, 1, 2, 3, 4, 5. So at 0, who comes? P4. At 1, P2 is there. At 2, P5 is there. At 3, who will come? P1 will come. And at 4, P3 will come. 1, 2, 3, 4, 5. So all of them comes like this. Okay. And so now let's start the gun chart. So now initially, okay, only P4 is there. So P4 will execute. Okay. P4 will execute for one time unit because after one time unit, P2 will come. So we need to check whether the P4's remaining time and P2's time, which one is smaller. So first P4 will execute for one time unit okay, until P2 comes. So how much is the remaining time of P4 after by the time P2 comes? What is the remaining time of P4? 5, right? Because
P5.
P4 have executed for one unit. Now, what is P2's time? It is 4. P2's is 4. So 5 is greater than 4, right? So we will schedule 5 is greater than 4. So we will preempt P4 and we will schedule P2. Okay. Now P2
Yes.
will execute. P2 will execute and at time unit 2, P5 is coming. Okay, so we have to see when P5 comes, what is the remaining time of P2. So P2 will
3.
execute for one time unit. So P2 executes for one time unit, 4 minus 1, which is 3. So the remaining time of P2 is 3 and the newly arrived process is P5. P5's time is also 3. So we will not go for any um, what yeah any preemption because they are same. Okay, so P2 will execute. P2 will continue for the next one unit because at time 3 P1 is coming. Okay, 0, 1, 2, 3. Now at 3 who have come?
Excuse me,
P1
ma'am.
has come. Huh.
Ma'am, after P2, why P5 is not coming for execution?
P2 is not completed yet. P2 is not completed execution, right? See, we preempt if the newly arrived process have shorter burst time. Now, when we checked here, when we checked at the end of time unit 2, that is when P2 is there is executing and P5 came. So we saw that both of them have the same burst time. The remaining time of P2 and the burst time of P5 were same. So we are not going for a preemption here. So we will make P2 to run for one more time unit because next time unit may P1 is coming. Okay. So
Yes, ma'am.
at time unit 3, P2 have executed 2 time units. So the remaining time for P2 is now 3 minus 1, which is 2. And at time unit 3, we have P1 also in the ready queue. We have P1 also in the ready queue. P1 is also there in the ready queue. We have 1 is there. We have P5 is there. We have P4 and we have P2. All of these people are in the ready queue. Now, of these, who is having the smallest? So, how we have to see is at time unit 3, what is the ready queue? Ready queue mein who all are there? So, we have P1, we have P2, we have P4 and we have P5. And what are the burst times? P1 is 1, P2's remaining burst time is 2, P4 ka remaining burst time is 5 and P5's burst time is 3. Now this is the state of the ready queue at time unit 3. So now P2 is currently running. Now does the ready queue have any process whose burst time is less than 2?
Yes, ma'am. P1.
P1 is having less than. So now we will preempt P2. We will take P2 outside and we will give the CPU to P1. So P1 will come here. P1 will execute for 1 time unit. Okay. So P1 is now done. P1 is done. Now at time unit 4, P3 have also come. Now 2 is also available. P3 is also now available in the ready queue. So now P1 have completed its execution. Now we need to choose one among these 4. This is 2, this is 2, this is 5 and this is 3. Whom should we choose?
P2.
Okay, let's choose P2. So now everybody is there already. Now all the processes are in the ready queue. So now we can choose it because after this time unit, no new process is coming. So we don't have to go for a preemption. Now it will become a normal SJF. Okay. So we go for P2. P2 will execute for 2 unit. After that P3 will execute for 2 unit. Then P5 will execute for another 3 and then P4 will execute for 5. Okay.
Yes,
So
ma'am.
P4 will execute, P4's completion time is 1. Okay, P4's completion time is 1. P3, P2, we can get rid of this 3. 3 plus 1, 4. 4 plus 2, 6. 6 plus 2, 8. 8 plus 3, 11. 11 plus 5, 16. Okay, so this is the Gantt chart of this scheduling. Okay. Now, when preemption comes, using the formula to find the waiting time will be easier. Okay. So, can we maybe we can see one more question. Is this clear?
Yes, ma'am.
Okay. Maybe quickly one more, and then we need to go to the previous year questions also. P1, P2, P3, P4, P5, and P6. So the arrival time, burst time, and remaining time. Okay, so the arrival time is 0, 1, 2, 3, 4, and 5. Burst times are 7, 5, 3, 1, 2, and 1. Okay. So their processes are coming in the order 0, 1, 2, 3, 4, 5, 6. So after every until 5, time unit, we have to check whenever a new process comes to the ready queue, we need to check whether the remaining time of the current process is less than the newly arrived processes. So let's start from 0. Okay. So 0 only, who is there? P1 is there. P1 will execute, and P1 will execute for one time unit because at time unit 1 P2 comes. So we need to cross check. Okay, so it will execute for one time unit. Then what is the remaining time of P1? 6,
6.
correct? Yeah, so at time equal to 1, 5 is also available. So now these two are in the ready queue. 6 is greater than 5, right? So we will preempt P1 and we will execute P2. Okay. So after P2 starts executing, in another one time unit, P3 will come. So P2 will execute for one time unit, and we again have to check because now P3 has also come to the ready queue. So how much is the time remaining time for P2? P2 executed for one
4.
time, 1
4.
millisecond. So it is 5 minus 1, which is 4. And we have P3 also in the queue, right? So P3, 4 is greater than 3. So we preempt this P2 and we give CPU to P3. Now P3 will again execute for one time unit because at time 3, P4 is coming. Okay. So P3's remaining time will be 3 minus 1, which is 2. And P4's time is 1. Now we have 1, 2, 4 and 6 in the ready queue. All these people are 1, 2, 4 and 6 are in the ready queue. So who is having the smallest burst time?
P4.
So we will again preempt P3 and we give the CPU to P4. Okay. P4 will run to completion because it needs only, by the time P5 comes in the next time unit, P4 will run to completion. Okay, P4 is done. Now at time unit 4, we have P5 which is 2, we have P3 which is 2, we have P2 4 and P1 6. So we will choose
P3.
P3. Okay, now P3 will execute for one time unit because at time unit 5 again P6 is coming. Okay, P3 will execute for one time unit. Now the remaining time is 1 for P3. And the P6 time is also 1. Since they both are the same, we make P3 continue. We will not preempt. P3 will continue and P3 will run to completion. P3 will run to completion. Okay. Now P3 will, we have one here. P3 is also run to completion. So this is done. This is done. Now we are left with 1, 2, 3, 4 people in the ready queue. Now everybody have arrived. Okay. By now everyone have come. Now we just need to schedule it in the increasing order of burst time. So now whom should we schedule? Who is having the smallest burst time?
And P6.
P6 for one time unit. Then
P5.
P5 for 2.
P2. And then P1.
So P1 1, P2 is 1 plus 1 2, 2 plus 1 3, 3 plus 1 4, 4 plus 2 6, 6 plus 1 7, 7 plus 2 9, 9 plus 4 13 plus 6. Correct? So this is the Gantt chart. Now from this you can find the turnaround time and the waiting time. Okay. Okay, now let's see the round robin scheduling. So this was the preemptive scheduling. Round robin scheduling is also a preemptive scheduling scheme. So here what happens is we give each process a fixed time. Okay, we don't look how much burst time it require and all that. We don't sort them, or we don't give them in the increasing order of burst time or anything like that. We will have a fixed time unit called time quantum, or time slice. We call it time slice. Okay. And this slice will be given to each process in the first in, first out order. Okay. So we have the ready queue. We have the ready queue. Processes comes P1, P2, P3, P4. Like this process will come. Then what we do is we take the first guy who came to the ready queue. We give him, like for example, if the time slice is 2, time slice is equal to 2, we give 2 units time for P1. P1 will execute for 2. Let's, for easiness, you assume 2 is 2 millisecond, or maybe 2 second is too much to assume. Assume that 2 millisecond, okay, is the time slice. So we give 2 millisecond CPU, we give P1 the CPU for 2 millisecond. After 2 millisecond, a timer interrupt will come. After 2 milliseconds, there will be a timer interrupt. Then timer interrupt will preempt P1. So P1 will go back to the ready and P2 will come in. Then P2 will be given 2 milliseconds. Then after 2 milliseconds, again the interrupt will happen. Context switching will go happen. That is, P2 will go to ready state and P3 will come to running state. It will again run for 2 milliseconds. Then after 2 milliseconds, P3 will go back to the ready state and P4 will come to the running state. It will run for 2 milliseconds, and this will continue until all the processes gets this much time. One round, all of them will, for example, we had only till P5 or P6. Okay. So P5 will be given to and P6 will be given to. Once this is done, once all the processes are done with one round of 2 millisecond, again we will start from here. Okay. So how it happens is, so P1, so we have the ready queue like this, right? So P1, P2, P3, P4, P5, P6. So first P1 will be given. So P1 will be removed. So P1 will be in the running state. Then after timer interrupt, P1 will be moved to ready queue. Okay. Now who is in the front of the queue? P2 is there. P2 will be given. Okay. Now P2 will go to running. Then timer interrupt. Then P2 will go to running. Then P3 will be running. We remove from the queue and we give it to running. Now once the timer, then the time slice is done, we'll put P3 into the queue. Now P4 will go to running. Now after the interrupt, P4 will go to the queue. Then P5 will go to running. After that, P5 will go to the queue. Then P6 will running. P6 will go to the queue. So like this it will come. So in the next round again P1, P2, P3. Now after that, suppose P1 after this iterations, P1 got the running again. Now P1 needed only one more time unit. We are giving 2 millisecond of that. P1 needed only 1 millisecond. So P1 exit. P1 will complete if the process is done with the execution, it will complete and it will exit. So we would have removed it. Then once the process exit, we will not add it back. Okay. So then P2 will get the CPU. Now if P2 needs more time, P2 will go to running. It will run for 2 milliseconds and then it will again go back to the ready queue. So this continues until all the processes completes to execution. Okay. This is how the round robin works. Is this clear?
Yes, ma'am.
Quickly see some examples. One quick example. Okay. All right. So we have P1, P2, P3, P4, P5. Right. Arrival time. This is first time. 0, 1. So here the time slices 2 units. Okay. So initially at time 0, okay. So at time 0, so the ready queue is like this. We have P1 at 0, P2 is at 1, P3 comes at 2, P4 comes at 3, and P5 comes at 4. Okay. So initially when we start, P1 will be given 2 time units. So P1 will be given 2 time units. Then P1 will go back to the, sorry. So initially I cannot just like that do it. So after P1 is done, we had only P2 and P3 in the ready queue, right? We had P2, P3 and P1 will get added here. Okay. So P1 will go back. So now P2 will get the time unit. So P2 will run for again 2 time units. Okay. Now when P2 is done, we all P4, P2 is there, P3 is there, P1 came, P4 came when it was 3, and P5 also came. By 4, P5 also came. Now P2 is done with executing. So P2 will go here. Okay. Now P3 will come. P3 will execute for 2 time units. Okay. So P3 is executing. Once P3 is done, P3 will go back. Now who is there in the front? P1 is there. P1 will execute for another 2 time units. Okay. Now after P1 is done, P1 will again go. Now P4 will get for 2 time units. Then P4 requires only 2 time units. So once P4 will not go back to the ready queue again. Okay. So P4 will exit. So P4 is done. Now P5 will get the again for another 2 time units. P5 will get for 2 time units. Okay. So P5 will go back here. After that P2 will come. Now how P2 is executed once and P2 needs only 3, right? So now on P2 will execute for 1 time unit. And with that P2 is done.
मैम आफ्टर P5 will P1 and P2 2 भी पहले आ सकता है या P2 ही पहले आएगा for execution after P5?
इस order में ही आएगा. I mean it will come in this order only. The order in which we are put them in. ठीक है. So now P2 is done. Right? This P3 required only one, so I think I did a mistake by bringing P3 here. P3 is already done here itself because it needed only one time unit. So yeah, here when we gave, no, yeah, it was done here. So P3 was not needed to be added to the queue. This is one time unit. Okay, that was a mistake. Okay, so now after P2, P1 is there, right? P2 is done. Now P1 is there. P1 already executed for 2 plus 2, 4. Now one time unit is left because its total time is 5. And after that, so 11 plus 1, 12. My God, 30 and 40. So this is how round robin works. Confused?
Excuse me, ma'am.
Yeah.
Ma'am, also explain what is average response time.
Average response time is the same as average waiting time, no?
Ma'am, it is always
So
the
it's
same of
like
average.
it's like the first time when it gets the CPU. That's what we normally take response
Ma'am,
time because
can you
otherwise
give
it must be.
example of this question
It's
also
already
including?
there in the. I think sir slide में तो it is there, right? Response time. It is mm, okay. Let me see. Response time. Yeah, so when we have this preemptive scheduling, right? So waiting time will include like, for example, if you see here, here P1 got the
Ma'am,
CPU
your
first.
screen is not showing here.
Acha, okay. Did I leave the call? Yeah. It's visible now?
Yes, ma'am.
Yes, ma'am.
Yeah. So with response time, for example, okay, let's see first waiting time. Okay. So for P1, if you see here, here the waiting time for P1 is 0. Okay. But P1 doesn't go completes here, right? After that, P1 gets the CPU here only. Correct? Sorry, where is P1? Sorry, oh, P2. Sorry, so P1 gets the CPU next here. So from 2 to 5, P1 is in the waiting. So 5 minus 2, 3 is waiting time. Again, from to this time, like 12 minus 7 is again waiting time for P1. Okay, so we will include all these with the waiting time. But with average response time, we see when that process is getting the CPU for the first time. Because we are assuming that in the first burst itself, some response will be given. So response time is computed like when the first um, slice of CPU is given to that process. So how long does it had to wait for that first slice? Okay. So if you see here for P1, it didn't had to wait at all, right? So for response time, for P1 it is 0. Now P2, what time did P2 come? P2 came at 1, correct? And it got the CPU at 2. So 2 minus 1. Now for P3, P3 came at 2, but it got the CPU at 4. So 4 minus 3, sorry, 4 minus 2 plus P4 came at 3, got the CPU at 7. Oops. 7 minus 3 plus P5 came at time unit 4, it got the CPU at 9. So 9 minus 4. So this you sum up, you will get the average response time. Okay.
Yes, ma'am.
It's 7:30. I think we should look at the previous year's question papers now. So I will copy paste the questions in the chat. You can, okay. I'll read it out loud also. I don't have time to type it in. Yeah, so the data structure best suitable for implementing round robin scheduling is a stack, queue, list, and an array. Data
Ma'am,
structure
Q.
for round robin scheduling. So it is queue. We saw, right? Why is it? So we dequeue from one end and we enqueue it in the other end. We want it to follow the first out order. So queue is the one which follows that. So the next question is what does turnaround time means? What does turnaround time means? Time from the process enters the ready queue to the time it starts execution. The difference between arrival time and the completion time of the process. Time taken from start to completion of IO. Time a process waits in the ready queue.
Ma'am, the difference between arrival and completion time.
Yeah, so turnaround time is the difference between the arrival time and the completion time. So between this, how long does it execute, how long does it wait, all are incorporated. So that is turnaround time. So yeah, the answer, the second one is the answer here. Now, next one. This is a match the following. It won't come properly in the chat. So A is order of n scheduler. The other is order of one scheduler. Time slice of a process. Time slice of a process. D is dynamic priority. So has two run queues to prevent starvation set based on priority of the yeah. So what is the answer here? So order of n scheduler. Order of n scheduler.
Not
How
stable.
it is not
Option 4.
scalable. Yeah, it is not scalable. So it looks into the ready queue. It scan the ready queue and then it chooses. So as n increases, its performance goes down. So order of one scheduler,
Has 2
it
run
have
queues.
yeah, we have active ready queue and expired ready queue. Then time slice of a process is
Set
set
based
based
on
on the
time.
priority of the process. And dynamic priority
On
is
average.
set based on the sleeping time. Okay, so A4, B1, C2, and D3. Now this I will copy paste. Preemption is yeah. So the question is preemption is forced deallocation of the CPU from a program which is executing on the CPU. This release of CPU by the program after completing its task. Option 3, forced allocation of CPU by a program to itself. And 4, a program terminating itself due to detection of an error.
Ma'am, option number A, forced deallocation of CPU.
Yeah, so preemption happens when the process is executing, but either a new process came which takes lesser time than this, or if the time quota time slice expires, that is when we forcefully take out the CPU. So it's forced deallocation of the CPU from a program which is executing on the CPU. Now the next is which of the following is not non-preemptive? FCFS, round robin, SRTF, and ideal
Ma'am,
fair
FCFS.
scheduling. So this is the non-preemptive one. State the true or false. System can have more than one scheduling algorithm.
Ma'am, true.
Yeah, so this is true. Like in multi queue scheduling we have seen, right? So it is possible. Now the next one is, okay, I can't write. Choose. Tell if each of these statement is true or false. There are two statements given. So, yeah. Okay. Shortest remaining time first algorithm is not practical. So there are two statements given after that. State whether they are true or false. Its time complexity is huge, which makes it unsuitable for real system, and it requires knowledge of the burst time, which is not easy to predict. Which of them is correct and which of them is false? Here, which is true and which is false? So the statement that the complexity is huge and which makes it unsuitable for real
Ma'am,
systems
it
is
is false.
false. Yeah. The second statement that it requires knowledge of the burst time, which is not easy to predict, is true.
I'm true.
Yeah. So that is true. Now, with respect to the table, okay, there are two problems which is based on this question. Okay, let me quickly. So we have P1, P2, P3, P4, and P5, and we have arrival time and close time. Arrival time is 0, 2, 3, 4, and 10. Burst time is 2, 1, 2, 3, and 10. Okay. And so what is the schedule length of the following process? If we use schedule length for FCFS. So let's draw the Gantt chart quickly. So who have come first? P1. P1 have come. P1 takes 2. After that, P2 is there. P2 takes 1. By then P3 comes. Yeah, P3 comes. P3 takes 2. 5. So by then P4 is already there. Then P4 comes and P4 executes for 3. Then P5 is not there. So for 2, the CPU will stay idle. And after that, P5 comes and it goes to completion. So total schedule length is from here to here, which is, 10 plus 10, 20. The schedule length is 20, 10 units, okay, to complete all this process. Now, based on the above, there is another set of questions. Tell which is true or false. Or true or false. So the option is the order of execution is same in FCFS and SRTF. So for the above table, they are asking if the order of execution is same in FCFS and SRTF. We have to state whether this is true or false.
Ma'am, is it false?
You have to do it and see only then you can claim. Just because they are two different algorithms doesn't mean it is always it will give a different output always.
Okay, ma'am.
Okay. So you have to draw the Gantt chart and see. The average waiting time is same. So the question is which of the following is false? Okay. And this question is with respect to the above table. The same scheduling, like the process arrival table is the same, but we need to see if SRTF, if it is SRTF, how it would be executing. Okay, so if it is SRTF, so at 0, P1 will start execute. Then P1 will execute for 2 time unit. P2 is coming. So P1 will complete the execution. Then P2 will come. P2 will come. So if you see here, P1 completes the execution by 2. Okay. And at 2 only P2 is coming. And P2 is having a burst time of 1. It executes at 1, and by the time P3 comes to the queue, P2 is done. So now P3 will go, P3 will start executing, and P3 completes at 5, but P4 is coming at 4. Okay. So, but P3's total burst time is only 2. So when P4 comes in, P3's shortest remaining time will be 1 unit. So, preemption will not happen. P3 will run to completion. P3 will complete. Then P4 is will be, because P5 comes very late. By the time P4 will be done, and then P5 comes. So the order is same. Okay. So this is true. Now average waiting time is same for SCFS and SJF. So if you see SJF also will have the same order, because first P1 comes. P1 is the only in the queue. Then P2 comes. So P2 is the only one in the queue. And when P3 comes, P3 is the only one in the queue. So in between, even if P4 comes also, it is SJF. So no preemption will happen. Then after P3, P4 is the only thing in the queue, and P5 comes very late. So the order of execution for all the three is the same. Since the order of execution is the same for all, their waiting time is also same. Okay, so this is same, and this is, we know it is idle for 2. So this is, all these are true. So this is the actually answer. Correct answer is none of the above. These statements are all true, so they are not false. Okay.
Yes, ma'am.
Yeah, another question is again on scheduling. At least 1, 2, I have to. Okay. So here we have A, B, C, D, A, B, C, and D. 0. Arrival time is 0, 0, 0, 0. And burst time is 4181. 4181. Okay. Using round robin scheduling. RR scheduling.
Ma'am, what is the time slice?
1 unit. Okay. What is the time at which process A completes execution? Okay, so all of them have come at the same time. So let's take the order as ABCD itself. Okay, so 0, A will execute for 1, B will execute for 1, B will complete in that, C will execute for 1. Sorry.
Ma'am, A will complete its execution at 9.
Okay, let me do this. Then C will, and then D will also complete. Okay. After that, A, B, A, D. 1, 2, 3, 4. And then D will be executed. Okay.
Here will
Fine.
be AC after ABCD. There will be AC will be in execution, not D, because D has one.
Oh, sorry, it is C. Instead of D, it is C. Sorry. Okay. 1, 2, 3. And this will be 5 for the value. Okay, so it is 9. Okay. Actually, options were given. That's fine. Okay. Okay, there is one more question. Consider three processes P1, P2, and P3 with arrival time 0, 1, and 3, and burst time 6, 5, and 4. Okay. So, what is the order of completion? In SJF and RR. Okay, so let's take shortest job first. So initially, when we start at 0, we have only one process P1 in the RR with time slice 2 unit. Yeah, so in first let's see SJF. Okay. So initially when we start in the ready queue, there is only P1. So P1 gets scheduled. So SJF is non-preemptive. Once scheduled, it will run to completion. So this P1 will run for 6 time unit. So after that, we have both P2 and P3 in the ready queue. Now of P2 and P3, P3 have shorter burst time. So P3 will be scheduled and it will run for 4 time unit, and after that P2 will run. Okay. So for 5 time units. So it is 10 and it is 15. This is for SJF. So the order is P1, P3 and P2. P2 for SJF. So now let's see for RR how it is. It is a so initially we have the ready queue. We have only P1. So P1 is here 0. Okay. So P1 executes for 2 time units. Like it is given as 2 for 2 time unit. Okay. Now by the time P1 finishes, P2 is there. Okay. P2 is there in the, so at time equal to 2, P2 is there. So P1 is moved here. Once P1's complete execution, P1 is moved back. P2 is there. So P2 will start the execution. Okay, P2 will execute, and by after like 1 time unit of P2's execution, P3 will come into the queue. Okay, so P2 will run for another 2 and it will be preempted. So P2 is done. P2 will be moved back to the this one. Now after that, P1 will be given the CPU. P1 will run for again another 2. Okay. Now P1, then P1 will go back to the ready queue. P3 will be given 2 units. Then P3 will go back. Okay. Then now P1 will be, now who have to execute? P2 has to execute. P2 will go back. So 4 plus 2, 6. P2 needs, so how many? 2 plus 2. Okay, 4 and 2 plus 2. Yeah, now P1 will execute for another 2. And after this, P1 is done with its quota. So P1 is completed now. Hmm? Now P1 will not go back to the ready queue. Now P3 will come. P3 already got 2 here. Now only P3's execution time is 4. So again another 2 is given. So P3 will complete here. It will not go back to the queue. Now P2 will run for another 1 time unit and P3 will complete. P2 will complete. So who completed first? P1, P3 and P2. So this is the order in round robin also. Okay. So,
Yes.
right. There is one more query, just a minute. Mm, One more last question we'll see and yeah, so one question here. It's a long question. Consider 3 processes with arrival time 0 and burst time of 10, 20 and 30 respectively. Okay. Each process first 20%. So this is not burst time, sorry, execution time. Execution time. First 20% exit time doing IO. Next 70% time doing computation. And last 10% time doing IO. Yeah. So OS does it is remaining compute time first. Scheduling algorithm. Assume that all IO operations can be overlapped. So what percentage CPU is idle? This is the question. Okay. So this is slightly different from the questions that we have seen. So let us see P1, P2, P3. So we are given with the total burst time. Okay. Total. So this burst time comprise of the IO and the CPU burst. So arrival time, let's ignore because all of them have come at the same time. So this is 10, 20 and 30. Now of this IO, CPU burst and again IO. So this total time is split into three. The first 20% of the execution time is spent for doing IO. Then the next 70% is for computation, and then the next 10% is for again IO. So 20% of this 10 is used for the first IO. 20% of 10 is 2, 70% of 10 is 7, and 10% of 10 is 1. Okay. Same way, 20% of 20 is 4, 70% of 20 is 40, and 10% of 20 is 2. 30 is the total execution time, of which 20% of 30 is IO, which means 6 is IO. Again, 70% is CPU burst, and the last 1% is again IO. So this you can compute, right? So I think you know this. How do you compute? That is 20%, which is 6. Okay. So this is how
Yes,
you
ma'am.
compute. Yeah. Mm. Oh no. Okay. Okay. So now all of them have come at the same time, right? And it is like we have the shortest remaining compute time first. So if you see, luckily this is in the same order. Okay. So initially, there will not be any preemption because all of them came at the same time, and we have the 7 is less than 14 and 14 is less than. Saying is initial 10% is um, IO. Okay, IO time. So that time the CPU will be idle. So initial 10% of the process 1, that is 2. So 2 time units, this uh, IO will happen. Now we are first scheduling P1. So P1 will spend 2 units on doing IO. So that 2 units the CPU will be idle. Okay. And P2 and P3's IO can happen parallelly. So CPU only we need to schedule it whenever the CPU becomes free. But IO we can schedule all of them together. So we initially schedule the IO for P1, um, IO for P2, and IO for P3. Okay, so this is 2, this is 4, and this is 6. Okay. Now, after this 2 millisecond of IO, CPU of 7. So P1 will execute for 7 unit. Okay. Then, so 7, this is 2, this is 9. Okay. So by now, by the time P1 again goes for its last 1% IO, P2 is done with its initial IO, correct? P2 is done with this initial IO. So P2 will come and start running. Okay. So P2 will run for another 14 units, which is 23. Now P2 will go. So here P1 is going for its IO. Now P2 will go for its last IO. But by the time P2 completes, P3 is done with its initial IO. P3 gets scheduled and P3 will run for 21. Okay. And okay. Now P3 also have a last leg of another 3 units IO. So that will be done. So this is idle for 3. This is the P3's IO. So CPU is, so this is when P3's IO is happening. Okay. So total execution time is from 47, right? Total execution time is 47, of which CPU stayed idle from 0 to 2 and 44 to 47. So CPU stayed idle for 2 plus 3, 5 time units. The total time it executed is total time it executed is 47. So utilization is 4 by 47 into 100, which is 10 point that you can find out. Okay, so this is another way of asking the questions. Okay. Yeah, so I think we are done. I think we have already overshoot the time. So maybe any doubts?
No, ma'am.
And then I will close the session.
Yes, ma'am.
Okay.
Thank you, ma'am.
Okay. Yeah. Thank you all for joining. Thank you.